Okay, we're going to talk about Le Chatelier's principle and what affects changes in the position of an equilibrium. Okay, now Le Chatelier's principle, you don't have to know it strictly speaking on the specification, but it helps if you do. It says, whatever you do to a reaction at equilibrium, the position of the equilibrium will move so as to oppose the change. So that means if you've got a mixture of something that is at equilibrium and you make it hot, what it will do is it will try and make it cooler. It won't succeed in making it cooler, but it will try and make it cooler. Now, how it can do that? Well, it can move in the endothermic direction. Now, we can use this reaction here between brown gas, nitrogen dioxide, and it exists in equilibrium with N2O4, which is it's not such a dark brown color, it's a very pale yellow color. So you can have an idea by looking at these two gases in a tube. You can tell how much of the NO2 you've got and how much of the N2O4 you've got by looking at the color. Now, this reaction, it so happens in the forward direction, I think it is exothermic. And in the backward direction, it must be that it's endothermic. Okay, so we'll bear that in mind we'll see to explain our observations here. So what we've got here I'll make this a bit bigger, is we've got a boiling tube and put a cork in it and filled it up with NO2, and it quickly reaches an equilibrium with N2O4. Now, if we get one of the boiling tubes, at first they're going to look the same color because they've both got the same amount of gas in them. And you take one of the tubes and you put it into hot water. You'll notice that it goes darker brown, okay, in the hot water. And if you put the other one in cold water with some ice in it there, it goes much paler brown. Just to show that this is due to a change in position equilibrium. If you swap the tubes about, then they will, whatever tube it is that goes in the hot water always goes the darker brown. So that tells us when we put it into hot water, so when we try and make it hot, we get more NO2 and we get less N2O4. You can tell that from the color. And why is that? Well, it's because, according to Le Chatelier's principle, if we try and make it hot, it will try and make it cold by moving in the endothermic direction. Okay, so conversely, if you try and make it cold by putting in ice water, it will try and warm it up by moving in the exothermic direction, and it will go paler. Of course, it doesn't do anything to the temperature of the water, but it just tries to. And so Le Chatelier's principle is a very good way a very helpful way we can predict what's going, how changing temperature will affect the position of an equilibrium. Okay. Right, so we can see the effect of temperature. Let's have a think about if we change the pressure, that will also change the position of equilibrium. Now, what I've got here is this time, instead of putting the gas into a boiling tube, you put the gas into a syringe and you seal the end up. So you get a plastic syringe, you seal the end just by melting it. Right. Now, if you push the plunger in like I've done there on this one here, you can see that the gas becomes lighter brown. That means we've got less NO2 and we've got more N2O4 when we increase the pressure. Because when you push the plunger in, you've got to push it there, and you've got to hold it with your hand, otherwise it will just come back again. When you compress the gas that way, it actually goes paler, and that's a bit counterintuitive because you would expect if you squash it, this is all a brown gas here. If you squash it, you think it would look darker brown, because it's in a smaller space, but it doesn't. It actually goes paler brown because it affects the position of equilibrium. Now let's see how that's happening. We've got 2 NO2 gas and we've got N2O4 gas. Now we can see on the left hand side of the equation we've actually got 2 moles of gas, and on the right hand side of the equation we've only got 1 mole. So if we increase the pressure, Le Chatelier tells us that the reaction is going to try and decrease the pressure. What's the only way it can decrease the pressure is by making less gas molecules. Because of course, what causes pressure are the gas molecules hitting the side of the container. So, it's a simple rule of thumb is that when you increase the pressure, the equilibrium moves to the side with the fewest gas molecules. So let's have a look at a few other examples there. We can have a look at a few more example reactions and see how increasing the pressure might affect them. Right, so here is a very important reaction. This is how ammonia is made from nitrogen and hydrogen. This occurs in the Haber process, which you may have done yet. Right, so you get nitrogen and you get hydrogen gas equilibrium reaction. You will end up getting 2 ammonia, and they're both a gas as well. So if we increase the pressure here, what's going to happen? Well, on this left-hand side of the equation, we have got 1 mole of nitrogen and 3 moles of hydrogen. We've got 4 moles of gas. Whereas on the right-hand side of the equation, we've only got 2 moles. So if you increase the pressure, it moves to the side with the fewest gas moles, i.e. it will move to the side, so you'll get a higher percentage of ammonia at equilibrium. And when they make ammonia in the Haber process, they have to use a pretty high pressure to get a reasonable amount of ammonia in the mixture, to get a reasonable yield of ammonia. As the higher the pressure goes, the more ammonia you're going to get there. Let's look at another one. So we could have, this time we can have carbon monoxide. That reacts with hydrogen gas to form methanol gas. Okay, so on the left-hand side of the equation, we have got, and that's not balanced, so I need to put 2 hydrogens there. Okay, on the left-hand side of the equation, we have got 1 mole of carbon monoxide and 2 moles of hydrogen, so we've got 3 moles there. And on the right-hand side of the equation, we've just got 1 mole. So if you increase the pressure for this one, again, the equilibrium is going to move to the right. I.e., in other words, you're going to get more methanol at equilibrium. Just do one more. Let's do the reaction between methane. This is how hydrogen is made. Gas and steam, H2O gas. That's an equilibrium reaction. There you get carbon monoxide and you get 3 moles of hydrogen. Now this time we have got 1 mole of methane and 1 mole of water on the left hand side, so that's 2 moles of gas altogether. Whereas on the right hand side we have got 1 mole of carbon monoxide and 3 moles of hydrogen. We've got 4 moles. So if you increase the pressure in this case, the equilibrium will move to the left. So this reaction, if you wanted to get a lot of hydrogen, you wouldn't want the pressure to be too high to favor the forward reaction. Okay. So if we just let's have a think about this ammonia reaction. We go back to the temperature thing, what Le Chatelier says. Making ammonia, N2 gas and 3H2 gas gives you 2NH3, and in the forward direction this reaction is exothermic. And of course that would mean in the backward direction it would be endothermic. So what kind of temperature should you use to get lots of ammonia? If you want lots of this stuff, what kind of temperature should you use? You should use a low temperature, because the Chatelier tells us if we lower the temperature, the reaction tries to increase the temperature. And what's the only way it can do that? By moving in the exothermic direction. Okay,